Okay, so this is module 3. This is the start of module 3 for the Math Visions project. We're going to go through each task and each exercise. Each task and exercise section is going to be its own video. Without too much ado, let's go ahead and get started. So 3.1 is talking about the in-betweeners, which is going to be introducing to us the concept of roots and rational exponents. So let's get to it. This is a develop understanding task, which means that it's an introduction. This is where they're going to introduce a new idea. So it says, now that you've seen that there are contexts for continuous exponential functions, it's a good idea to start thinking about the numbers that fill in between the values like 2 to the second power and 2 to the third power in an exponential function. So what that sentence means is a continuous exponential function means that there's no breaks. So even though we usually graph functions by graphing their points and there's spaces in between the points, a continuous function recognizes that there are no spaces in between the points and that we could plug in or we could find a value when x is, for example, a number between 2 and 3, like let's say 3 or 5 halves or something like that. Right? If we could know what the value is for the function at x equals 5 halves, or even other rational numbers between 2 and 3, then it would be continuous, right? As long as there's not a space between values, we could always find more values between given values. So that's the idea that it's starting to put forth, is saying what happens when we look at exponential functions between the values of just integer x values. These numbers are pretty interesting, so we're going to do some exploring in this task to see what we can find out about these in-betweeners. That's why it's called in-betweeners. So let's begin in a familiar place. We're given an f of x table for inputs and outputs, and we're given all these x values here, and we're just going to complete this table. So we know if we substitute 0 in here, we're going to get 4. If we substitute 1, okay, that's going to give us f of 1 is equal to 4 times 2 to the power of 1. And 4 times 2 to the power of 1 is just 4 times 2, which is 8. Okay, f of 2 equals 4 times 2 to the power of 2, which is 4 times 4, which is 16. F of 3, 4 times 2 to the power of 3, which equals 4 times 8, which is 32. And f of 4 equals 4 times 2 to the power of 4, which equals 4 times 16, which is 64. So we've completed our table here. Now it says plot these points on the graph at the end of the task and sketch the graph of f of x. So we have here, so graph, we're just going to plot these points. So 0, 4 is already plotted for us here. 0, 4. We had one at 1, 8, which is here. Another one at 2, 16, which is here. Another one at 3, 32, which is here. And then another one at 4, 64, so which is all the way up here. It's up there. 464. Okay, and then it says sketch the graph, so we can just, it's probably going to look something like this. It's the standard curve of an exponential graph. It just curves up like this. Okay, let's continue. It says, let's say we want to create a table with more entries other than these entries. So we want more entries in this. Maybe with a point halfway between each of the points in the table above. there are a couple of ways that we might think about it. We'll begin by letting our friend Travis explain his method. So we're going to read about Travis's method for finding values in between the values that we already have. So let's read his method. Travis makes the following claim. If the function doubles each time x goes up by 1, okay, let's verify that that's true first of all. So x is going up by 1 here, and by 1 here, and by 1 here. So x is going up by 1. We can see that's x here on the table. So it's going up by 1. Is the function doubling each time? Yeah, I'd say it is, right? 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, and it continues on. So if the function doubles each time x goes up by 1, that's true. Then half that growth occurs between 0 and a half, and the other half occurs between a half and 1. So what he's suggesting is, for example, from 4 to 8, it's adding 4. So he says you can split that up into adding 2 and then adding 2 again. He says, for example, we can find the input at x equals a half. Okay, so that's between 0 and 1, by finding the average of the outputs at x equals 0 and x equals 1. So so let's do number 3. After having read that, we can complete number 3. Fill in the parts of the table below that you've already computed, and then decide how you might use Travis' strategy to fill in the missing data. So we've already completed these ones. We're just going to fill in. So we know 1 goes with 8, 2 leads to 16, 3 leads to 32, and 4 leads to 64. And now we have to use Travis' strategy. It's asking us to use Travis' strategy to fill in the middle values. So between 4 and 8, we want to find the average. So to find the average of two numbers, what we can do is add them together and then take the resulting sum and divide it by 2. So 4 plus 8 gives us 12. Divided by 2 is 6. And that gives us the number that's precisely in the middle between 4 and 8 arithmetically. So 4 plus 2 is 6, plus 2 is 8. 6 is in between 4 and 8. To find the number between 8 and 16, we can add the 2 together. That's going to give us 24. And then cut that in half, and that'll give us 12. And then we just repeat the process. So 16 plus 32 is 48. Divided by 2 is 24. And then 32 plus 64 is 96. Divided by 2 is 48. It says also plot Travis data on the graph at the end of the task. So let's plot this information on the graph. So here's our graph. Let me position. Okay, so we've already plotted a lot of these, but we haven't plotted these half values. So half and 6. So here's 0, here's 1, half is here, 6 is here. Between 8 and 16, so between these 2 points, we have 3 halves, and that is 12. That'll be here. I'm going to go ahead and label these. And then between 2 and 3, so between 2 and 3 here, this would be 5 halves. And we get 24. So let's put 24 in. It's 20, 22, 24. There. And then 48 between 3 and 4. So let's follow this line up. And we're going to put it here at 48, which is here. Okay, so that completes number 3. We've plotted Travis's data on this graph. So let's go to the next page. It says, comment on Travis' idea. How does it compare to the table generated in problem 1? For what kind of function would this reasoning work? Now, your comment is going to be unique to you. And so you should take some time and comment what you think. Some things to keep in mind would be the growth of the different tables, right? How does the growth of the table in function 1, or excuse me, exercise 1, compare to the growth from number 3? What do you see in terms of functions? Are we looking at linear, exponential, quadratic, or other? And you can comment on things like that. So I'm going to leave this for you. That is your opinion. Okay, let's continue. Miriam suggests they should fill in the data in the table in the following way. So we listened to the way Travis suggests to fill in the data, and now we're going to listen to Miriam. She says, I noticed that the function increases by the same factor each time x goes up by 1. So she is commenting, back to here, she's commenting that these factors are all the same, right? It's always 2. But it doesn't really, she didn't comment that it was always 2. She said it's always the same. So the 2 doesn't matter as much to Miriam as the fact that they're all the same. And then a little bit of vocab, factor, in this case. Notice she didn't say the same number. She said the same factor. Factor means multiplication. So she's noticing that it's being multiplied each time by the same amount. So each time x goes up by 1. And then she makes a comment about doing something like this last year. And I think this is like what we did last year with geometric means. And then she says, to me, it seems like this property should hold over each half interval as well. When she talks about this property, she's talking about this idea of the same factor. Okay, so it meaning each jump in x should be the same multiplication as long as the intervals are the same, in this case, half intervals. So that just means when x is going up by 1/2. So let's read number 5 here. It says, fill in the parts of the table below that you've already computed in problem 1. Okay, so we know that that's 8. We know that that's 16, 32, and 48. And, oops, excuse me, that's 64, not 48, 64. And then decide how you might use Miriam's idea to fill in the missing data. As in the table in problem 1, each entry should be multiplied by some constant factor to get the next entry. And that factor should produce the same results as those already recorded on the table. Use this constant factor to complete the table. Also plot Miriam's data on the graph at the end of this task. Okay, so what we're trying to find is a number that we can use, and we can multiply by the same number. So all of these would be the same. And it will not only land on the numbers we've already done, but it would allow us to find these numbers, which will be different than Travis, because Travis just found the number in between. This is more specifically, we're finding a number that will be the same factor each time. So this introduces us to the idea of rational exponents, because if you don't know what if you're not familiar with square roots and with rational exponents, then this question is not going to have an answer, right? 4 times a number times the same number again equals 8, right? That's what it's saying. It's saying 4 times blank equals 8. And these two blanks have to be the same number. That doesn't have an integer answer. It doesn't have a whole number answer. So what we can do to understand and to write what this number would be, we can do it in the context of breaking up a multiplication. So for example, we know that if we go straight from 4 all the way to 8, so we go from 4 to 8, we know that that's times 2. But since we're only multiplying, we want to go halfway, but in a multiplication sense, not in an addition sense. We want to multiply half of the 2. That doesn't mean multiplying by 1. It means we're going through half of the multiplication and then the other half of the multiplication. So the tool that we use is we use exponents, and we say that the number we're trying to multiply by is 2 to the power of 1/2. I'm actually going to write that over here. Okay, this is the big idea for this section. So 2 to the power of 1/2 means half of a multiplication of 2. Again, it doesn't mean 1. It does not mean 1. It does not mean 2 and a half. It doesn't mean 2.5. It means instead of multiplying by a complete 2, you're multiplying by a part of 2 in such a way that if you do it twice, it's like multiplying by a full 2. Now, some interesting things about this number. This number does not have a decimal representation that is accurate or that is precise. If you put this in a calculator, the calculator will give you a number that's very close. The calculator will do its best to give you an approximate value, but it will not give you this value. And in fact, the only real representation that we have for this number is in the context that I just described. So there's 2 ways to write this number. This is one of them, and it's one of the best ways to understand what the number represents. If you're craving an approximate value, you can think of this number as being around 1.4. Obviously, it's not 1.4 exactly because that would be a decimal representation, but that gives you an idea of how big this number is. Again, we do not have a way to precisely write this number other than this way. Right? If you write it this way, we understand that as half of a multiplication of 2. So if we take 4 and we multiply it by half of a multiplication of 2, we get 4 times 2 to the power of a half. Okay, and then if we multiply it by half of a multiplication of 2 again, that is going to be a full 2. And so then we multiply 4 times 2 halves, or a full 2, which gives us 8. And then we can multiply by that again, 8 times 2 to the power of a half. And then we complete that to 16 times 2 to the power of a half. And then 32, and then 32 times 2 to the power of a half. Like so. It says also plot Miriam's data on the graph at the end of this task. We're going to do that after we complete the rest, because the graph is the last page on this task. And this would be an approximate value. When we plot this data, it will be approximate because if we want to know about how big this number is, we can plug it into a calculator, and that would just be approximately how large it is. Okay, so I'll put a little star to remember to go back to that. Okay, let's go to number 6. What if Miriam wanted to find values for the function every third of the interval instead of every half? What constant factor would she use to be consistent with the function doubling as x increases by 1? Use this multiplier to complete the following table. So again, let's fill in what we already know. We know 8, 16, 32. We know that from 4 to 8 is a multiplication of 2. But we're going to take this multiplication of 2 and we're going to separate it into 3 smaller jumps, 3 smaller actions. So each of these would be 1/3 of a multiplication of 2. Not 1/3 of 2, but 1/3 of a multiplication of 2. So these would be multiplying by 2 to the power of 1/3. So this would be 4 times 2 to the power of 1/3. And then we'd multiply by 2 to the power of 1/3 again, and that would take us 2/3 of the way. So we get 4 times 2 to the power of 2/3. And then we multiply by 1/3 again. This would be 4 times 2 to the power of 3/3, which is a complete 2. 2 to the power of 3/3 is a full 2. That's why we land on 8. And then here we just repeat the process. 8 times 2 to the power of 1/3, 8 times 2 to the power of 2/3, and then a complete 2. And then 16 times 2 to the power of 1/3, and 16 times 2 to the power of 2/3. And then we land on 32. So question 7 says, what number did you use as a constant factor to complete the table in problem 5? We use 2 to the power of a half. That's our constant factor. This number does not have a decimal representation that's accurate and precise. So this is the we can approximate this as about 1.414. What number did you use as a constant factor to complete the table in problem 6? 2 to the power of 1/3. Again, same deal. We don't have a precise decimal representation, but we can get a decimal approximation of 2 to the power of 1/3 is about 1.2599. So that's actually 1.260. It's about 1.260, but that's an approximation. So give a detailed description of how you would estimate the output value f of x for x equals 5/3. This is for you to do, right? It's your job to put together what I've shown you, right, this idea, and to own it, right? Synthesize it in your own mind, restate it in your own words, and own this idea. Don't just memorize it, don't just copy it, but learn it and internalize it. And then you can do that by trying to answer this question. So this one is for you to try to answer. How would you estimate the output value for f of x when x is 5/3? Right? How would you estimate this output value? Right? Okay, so now let's go ahead and complete the graph. We want to complete number 5, which asked us to graph. So what we can do is we can do 4 times 2 to the power of 1/2, which is about 5.66. So a little bit more than 5, but not quite 6. So it's actually here. And then we can do it to the power of 3/2, which is 11.316. So a little bit higher than 11, not quite 12. It's a little bit lower. So far the numbers have been lower than what Travis got. Miriam's numbers are slightly smaller, right? Because Travis got 12 here. 3/2, 12. This was Travis's point, and Miriam is saying it's 3/2 and about 11.31. Okay, and then we do 5/2. This is 22.63. So this is 24. That would be 23. 22 would be about here. So slightly lower. Miriam's numbers are slightly lower than Travis's. And then we can go one more to 5/7 or 5/2, or excuse me, 7/2, which is 45. It's about 45.2, which is here. So again, this is Travis's point, this is Miriam's point. Okay. Now we're going to go ahead and complete some of the ready, set, goes so that you can check your work. You'll definitely want to try these first, so you should pause this video and work on them. And then if you get stuck, and if you really tried and you got stuck and you tried to figure it out by yourself, then you can come in and watch the video. But you shouldn't just automatically come in without trying it first and putting in a great deal of effort. So let's go through. Comparing additive and multiplicative patterns, the sequences below exemplify either an additive, which is called an arithmetic, or a multiplicative, which is a geometric pattern. Identify the type of sequence, fill in the missing values on the table, and write an equation. So let's go ahead and look at number 1. This sequence is doubling each time. So this one would be 64, this would be 128, and this would be 256. The type of sequence, because this is multiplying each time by 2, this is a geometric sequence. And the equation would be, we could write value. So the value of the term is equal to whatever term it is. No, it's equal to 2 to the power of whatever term. So 2 to the power of 1 gives us 2, 2 to the power of 2 gives us 4, 2 to the power of 3 gives us 8, and so on. So it's 2 to the power of the term. Okay, question 2. And from 66 to 50 to 34 to 18, we're subtracting 16 each time. So this is going to give us 2. This is going to give us negative 14. This is going to give us negative 30 and negative 46. Since we're subtracting, this is an arithmetic sequence. And the equation is the value of the term is going to be, we're subtracting 16 over and over. So we know we need minus 16t. We're repeating a subtraction of 16 by however many times. So if I plug in 1 in here, it would count as if I subtracted 1 already, one subtraction of 16. So when I plug in 1, I need the answer to be 66. So I need a value here such that when I plug in 1, I land on 66. So that's going to be whatever 16 more than 66 is. So that'll be 82. So 82 minus 16 times 1 would just be minus 16, and that'll equal 66. If I plug in 2 for the term, if I go for the second term, that means I will have subtracted 16 twice. And so that'll land on 50, and so on and so forth, right? If I plug in 8, it means I have subtracted 16 8 times. 82 minus 16 8 times is going to be negative 46. And so this is the equation. Okay, question 3. We go from 3 to 9 to 27, 81, and we're alternating negative, positive, negative, positive. So that means this is going to be negative, this will be positive, this will be negative. And it is multiplying by 3 each time. So 81 times 3 is going to be 243. 243 times 3 is 729. 729 times 3 is 2,187. And 2,187 times 3 is 6,561. So this is a multiplicative sequence. It's a geometric sequence. And the equation is the value of t is equivalent to negative 3 to the power of t. So if I substitute 1, it'll just be negative 3. If I substitute 2, it'll be negative 3 times negative 3, which negative times negative is going to be positive. And that'll be 9, and so on and so forth. And that will be that. Okay, for question 4, let's take a look. 160, 80, 40, 20. It's dividing by 2 every time. This is 10. This will be 5. This will be 5 halves. And this will be 5 fourths. So the type of sequence, it's geometric. It's dividing by 2 each time. And so this equation is going to start at 320 multiplied by a half t times. Right? So when t is 1, it's 320 times 1/2 one time, which is why we get 160. When t is 2, it's going to be 320 times a half and then times a half again. So the first time it would be 160, and then a half again gives us 80, and so on and so forth. Whatever the term number is would be however many times we multiply by half. Okay, continuing on. We have this sequence, which is adding 7, adding 7, adding 7. So we can continue this, add 7, add 7, add 7, and add 7. So these are all adding 7. This is an arithmetic sequence. And the equation is going to be the value of the term. 7 is being repeated, and it's adding 7 is being repeated. So we're going to tell the equation that we want to repeat the numbers, the addition of 7 by the term. And we want to land on -9 when we plug in 1. So that's going to be, we need a number that's smaller than -9 by 7. So that'll be -16. So when I plug in 1, it'll be -16 plus 7. That'll be -9. If I plug in 2, it will be -16 plus 7 twice. So plus 14. That gives us here, and so on and so forth. So these are some of the answers, and your equations might be slightly different, but these are just an example of how you could write those equations in there. Okay, let's continue on. Okay, this is the set. Nope, this is still the ready. It says use the graph of the function to find the desired values of the function. Also create an explicit equation for the function. So for number 6, find the value of f of 2. Find the value of the function, find the value of f when x is 2. So when x is 2 corresponds to, let's look at the scale here. So this is 5, this is 0. So 1, 2, 3, 4, 5. Yeah, these x's are going by ones. So find the value of f when x is 2. X is 2 right here. And the value of f, we can look, is going to be 2. So for question 6, we can say f of 2 equals 2. Okay, then it says find where the value of the function is 4. Right? For what value of x is f4? So we look for 4. We can look across. It's right here. And that x value is 4. So f of 4 equals 4. Okay, find the value of the function when x is 6. So here's x is 6 here. And if we find the value of that function, that's right there, which we look across, and that's 8. So we say f of 6 equals 8. It's right there. And then finally, find where the value of the function is 16. So we can look over here. 16 is there. And where is that? That is when x is 8. So f of 8 equals 16. What do you notice about the way that inputs and outputs for this function relate? Create an in and out table if you need to. This is what do you notice? So I'm going to leave this for you. What do you notice? There's a couple of things to notice here. What do you notice? So this is for you to answer. And then it says, what is the explicit equation of this function? So what we can see for this pattern is that it is doubling, right? So we can see this is 1, and then it goes to 2, and then it goes to 4, and then it goes to 8, and so on. So it's doubling, but it takes 2 jumps of x for it to double. So it doesn't double for each jump of x, it doubles for each 2 jumps. So what we can say is that the function is repeating this value 2 to the 1 to the half power times x. So when I plug in 2, it's like I multiplied 2 of these, so it's a complete 2. If I plug in 4, it's like I multiplied 4, and so that's like half, and half makes a full 2, and then another half makes another full 2. So there's 2 full 2s, that's equals to 4. So this is the explicit equation for this function. Again, own this, right? Internalize it. Don't just stop just because you know the answer now. Go back through, make it make sense to you. Okay, it has to make sense. And if it doesn't make sense, ask about it. Okay, you want to understand how this works. Okay, let's keep going. So over here to the set, fill in the missing values of the table based on the growth that is described. Okay, so it says for number 12, the growth in the table is triple at each whole year. So we can see this is year 1, it's tripled. Okay, so this would be times 3, but we're splitting it up into 2 jumps. So this would be 3 to the power of a half and 3 to the power of a half. So this would be 2 times 3 to the power of a half. And then we multiply by the other half, and that gets us 6. This would be 6 times 3 to the power of a half. And then we multiply by 3 to the power of a half again, and that gives us a full 3, which is 18. This would be 18 to the power, or times 3 to the power of a half. And then 18 times, we take this and we multiply it again, and that gives us 18 times 3, which is 54, I think. That looks right. Yeah, 54. And then this would be 54 times 3 to the power of a half. And then 54 times 3, which is 150 plus 12, 162. 54 times 3. Yeah, 162. That's right. Okay. What if the growth in, okay, so that's question 12. Question 13, the growth in the table is triple each whole year. So these are the same values as above. I'm noticing 0 is still 2, 1 is still 6. That means 2 is still going to be 18. And the only difference is, since I'm breaking this up into 3 jumps now, this would be times 3 to the power of 1/3 instead of to the power of 1/2. 2 times 3 to the power of 1/3. 2 times 3 to the power of 2/3. 6. 6 times 3 to the power of 1/3. 6 times 3 to the power of 2/3, 18. 18 times 3 to the power of 1/3, and 18 times 3 to the power of 2/3. Okay. And that finishes off 13. So now question 14, the values in the table grow by a factor of 4 at each whole year. So we can see that this is multiplying by 4, and we're going to split that up into 2. So we could say 4 to the power of a half and 4 to the power of a half. So this could be 2 times 4 to the power of a half. Now there's a number actually that already does this. So if I take multiplying by 4 and split it into 2 multiplications, that's the same as multiplying by 2 and multiplying by 2, because if I multiply by 2 and then multiply by 2 again, it'd be the same as multiplying by 4. So even though I can use 4 to the power of a half, that's the same as multiplying by 2. And that gives us this idea. 4 to the power of a half is 2. So sometimes these numbers do have integer values, and sometimes they don't. This is the first case we've seen where actually it does have an integer value. So we can just use 2. 2 times 2, which is 4. 8 times 2 would be 16, and then this would be 32. And this should be times 4, which it is. This should be times 4. So 32 times 2 is 64. 64 times 2 is 128. 32 times 4 is 128. 128 times 2 gives us 256. And 256 times 2 is going to give us 512. And this should be times 4, which it is. So that's our set. Okay, again, internalize it. Don't stop just because you know the answers. Make it make sense. Ask questions. Okay, and finally, we'll do this go. I'm running up against the clock here, so if I have to stop early, then I will stop early. So simplify the following expressions using exponent rules and relationships. Write your answers in exponential form. And it gives us an example here. So exponent rules is something that you will have picked up in around, I want to say it's around 8th grade, but I'm not quite certain on that. But it's definitely a previous year. So 3 squared times 3 to the 5th. That's 3 times 3 times 3 times 3 times 3 times 3 times 3. In other words, it's 3 to the power of 7. Here we've got 5 to the third power divided by 5 to the second power. So 5 times 5 times 5 divided by 5 and then divided by 5 again. You're dividing by 2 5s here because it's in the denominator. So that's going to just equal 5. Here we've got 2 to the power of -5, which means just divide by 2 5 times. So if you take, what does it mean when you divide by 2 5 times? That's the same as dividing by 32. If this doesn't make sense, please ask. And ask your teacher about this, and they can show you the pattern of how this comes about. 17 to the power of 0, that's going to be 1. Here we've got 7 to the 5th power divided by 7 squared times 7 to the 3rd power divided by 7 to the 4th. So in the numerator, we have 8 7s. In the denominator, we have 6 7s. So 8 7s divided by 6 7s is going to give us 2 7s left over. And so that's going to be 7 squared, which is 49. And then here for number 20, we've got, if we look here, this is 3 to the 5th multiplied by 3 to the -2. That's the same as dividing by 3 twice. And then we're dividing by 3 7 more times. So we've got 5 3s dividing by 9 3s. Which is the same thing as dividing by 4 3s. So 3 to the 4th power right here. Okay, and again, take time and internalize this, right? Think about it, ask questions, make connections. You should be able to explain why all of these are true. All right, everybody. I will see you next time for the next task.